To derive the acceleration for constant speed circular motion, there's two things we need to know first. One thing is that if you have a circle and you want to look at the arc length of this slide, making an angle theta over here, it will be just the radius times this angle theta for this arc length. And in this case, the unit for this angle should be radian. So with this definition, an entire circle should have a radian of 2 pi, because then r times 2 pi gives you 2 pi r of the circumference. So if I want to convert an entire circle, which is 360 degrees, to radian, that would be 2 pi. So this is the unit conversion between degree and radian. Another thing is that if you want to subtract two vectors on a graph, let me draw the xy coordinate. Here's my x-axis, here's my y-axis. If you want to subtract two vectors, let's say A and B, and then you want to see how you can go from A to B. If you go from A to B, this black vector will be A minus B. Or is it? It's going to be B minus A, yeah. So that if you add A with this vector, you get B. So this is the subtraction of vector on a graph. So if you know these two things, you are ready to derive the acceleration for circular motion. Now, when a thing is moving in circle, and initially it is at here, so this is the position at t, the velocity will be perpendicular to the position. At a later time, it will go to another position. Let's say this is rt plus delta t, and then it will also get a different velocity because the direction of velocity is changing, but the speed, which is the magnitude of the velocity, will be the same. So here is going to be vt plus delta t. Now, what we want to do for acceleration is to subtract these two velocity vectors, one at later time and one at earlier time. So to do the subtraction between these two vectors, we move them together. Let's say I don't need a circle, and we will move them together like this. So here's later, here's earlier. Okay, good. So according to the graphical rule for vector subtraction, if I want the later v minus the earlier v, I go from the earlier v to the later v. So this is going to be my change of velocity. So if I want the magnitude, it's going to be the same as this arc length. If the angle here is very small, and it is going to be small because we are taking delta t to be small, and a angle after a so small time is going to be small. And that angle will be the same as this one. Therefore, if I want the magnitude of delta v, I will just use the radius in this case, which is going to be the magnitude of velocity, which is the speed, times delta theta. Now, after some time delta t, the arc length here should be equal to the speed times the time that had passed. But we also learned that it is going to be the radius times this angle. So the radius times delta theta equals v delta t. And then we can replace delta theta with vr delta t and plug it in here. So the change of velocity will have a magnitude of vr delta t, and that is v squared over r. And if we want acceleration, the acceleration will be that divided by delta t, and we see we get rid of the delta t over here. So the magnitude of a constant speed circular motion's acceleration will be v squared over r. And because it is going backward, let me remove this 2. This is the position at that time, and if the delta t here is very small, this angle is also going to be 90 degrees. So the acceleration, which points the same direction as delta v, will be going backward compared to the position of the particle. So when a particle is moving in a circle, like this, and right now it is at here, the position and velocity will be perpendicular, and the acceleration will be perpendicular to velocity, which points toward the center of the circle.